by pi, we still get 0, don't we? That's just going to make it a little easier for me to look at. So divide by pi, I get x minus a fourth equals 0. What would this one become? X minus a fourth equals 1 over 2, 1/2, right? I'm basically just canceling all my pi's out. This is not, you don't have to do it this way. I'm just pointing out this is kind of, if the pi's kind of confuse you, you can kill them off in this problem by just dividing by pi. Are y'all okay? What's going on? Is this just a Monday afternoon or what? Is it, I mean, do you feel like a Monday? That's what I mean. Does it, like, I know this isn't the most exciting stuff in the world, graphing trig functions, okay?
It's just really hot.
Is it hot? Is it warm? Stuffy? No? Well, you have a sweater on. That could factor in. You all right with that step? Don't have to do that, but I'm just trying to make it a little easier algebraically by just killing all the pi's off. We can't always do this, but the fact that I have pi's everywhere allows me to do it. All right, this is just adding fractions, right? So here, x is 1/4. Here, x is, what's that? We'd have to add a fourth on both sides. So what's 1/2 plus 1/4? 3/4. Here, what's 1, and we're going to move that over, right? What's 1/4 plus 1? Don't say 1 1/4. Give it to me as a proper fraction or improper fraction. 5/4, 5/4. This one, add 1/4 to both sides. Right, we're getting a common denominator. That's what we're doing, right? We're adding these. We're getting common denominator. So this is 6/4. So 7/4. And finally, x is 2 plus 1/4. So what is that? Nine-fourths. Why are you whispering? Say it. Feel good about it. Say it. 9/4. All right, I'm going to draw it. Those are going to be my points, right? Yeah. Oh, I thought you were asking a question. No? All right, so here are my points. 1/4. And I'm going to put the other point over here, 9/4. Those are my two endpoints, right? The 1/4 and the 9/4. And then the point right in the middle should be this one, 5/4. And then in the middle of those two should be the 3/4. And in the middle of these two should be the 7/4. So there are my points. And I'm drawing a cosine function now, right? This is going to be a cosine function with an amplitude of 1/3, right? 1/3. So I'm just going to label here 1/3 up here, negative 1/3 down here. Where are my x-intercepts? Where are my x-intercepts? At where? 1/4? 5/4? 9/4? That's if it were a sine function, right? Remember, it's a what? It's a cosine, right? So it actually is going to be at the quarter mark, which is 3/4 and 7/4, right? And then did this cosine function get flipped? No, right? It's positive 1/3. So I should start, where's my highest point? It should be at that first point here at 1/4. It should be up here. And then at the 5/4, it should be down here. and my 7/4, where is it? At the x-intercept, then at my 9/4 back up here. And I'm going to draw my cosine function in here, like that. All right, what next? Those verticals, right? Those vertical asymptotes. And where are those going to be? At 3/4 and 7/4, because that's where I have x-intercepts on the cosine function. That's where my cosine function is 0, right? And 1 over 0 would be undefined, so I'm going to have this and this. Almost done. At this lowest point, put a dot, like that, like that. At this highest point, let's just draw this like this. You don't need to draw the other side. And then over here, draw like this. That is the graph of 1/3 secant of pi x minus pi over 4. All right? Do you feel like you have kind of a basic grasp of all 6 trig functions? Sine, cosine, tangent, cotangent, secant, cosecant? No? Yes, thank you. All right, so let's do a summary. I want to do a quick summary of all 6 trig functions. I want us to talk for each one about the different characteristics, all right? That way we have them all in one place. And then we're going to be ready to move on. So let's talk about y equals sine x. All right? As a quick summary of y equals sine x, a quick graph of this. We should all be very familiar what those points are, right? What's the domain? What are you allowed to plug into this? Anything you want. Yeah. Negative infinity to infinity. And what is the range of this function? What comes out of this? Everything? Only between -1 and 1, right? So this should go -1 to 1 for the standard sine function. Okay, I haven't moved it or stretched it or anything. So the range is -1 to 1. -1 to 1, right? And what's the period of this? What's the period of this standard sine function? That means what's the distance to complete one cycle? 2 pi. And the amplitude of this is 1, right?
Yep.
Okay, that's what the basic sine function looks like. How about cosine? Well, cosine, the only difference here is a slight difference in our picture, right? We have x-intercepts here instead of here. And it goes like this, down, back up. That's 1, this is -1. So what's the domain of this? Everything, right? What's the range? -1 to 1 again, right? What's the period? 2 pi. What's the amplitude? So isn't this exactly the same? Right? So it's everything that was over here, exactly the same on this. Domain, negative infinity to infinity. Range, -1 to 1. Period, 2 pi. Amplitude, 1. All right, let's talk about tangent. The tangent function has 2 vertical asymptotes, important points. Where do those happen for tangent? It hits in the middle, right? At 0? Where are the two verticals? Pi over 2 and negative pi over 2. You need to know that. All right? And then the picture looks like this. All right, here's where things start to get a little weird. What's the domain? Oof. Tricky, tricky, tricky. Okay, you ready? Pay attention. The domain, well, this keeps repeating itself, right? So like if I were to draw this out here, I've got vertical, vertical, it does this, and it does it again, then another vertical, then it does it again, another vertical. And there's a bunch of places where I can't plug numbers in, right? There's a bunch of places. So I think the best way to understand the domain is to go back to the unit circle. Let's go back to the unit circle. Instead of looking at this graph, let's go back to the unit circle. Tangent, by definition, is which coordinate divided by which coordinate? Y over x, right? So we know that tangent of some angle is the y divided by the x. We're always going to have a problem with this when x is 0, right? When is x 0 on our unit circle? Where? At what angles is x 0? Pi over 2 and 3 pi over 2, right? Those are the two places where we would have problems. So we want to make sure that these two angles never show up, right? You can see them right here. Here's pi over 2, right? We had a problem here. The next one would be at 3 pi over 2. And then there would be another one, another one, another one, right? And then backwards, negative pi over 2. That's this one, but if you go backwards. So part of your exam review is, can you solve this equation? Like, can you actually figure out what all these solutions are? And we did this once in class. How do you represent all the angles that are coterminal to these 2 points? So the way I explain this in class is, what you do is you notice that you can start by going there. That's the angle pi over 2, right? And then to get to this angle, how much would you have to add? You'd have to add a half rotation, so you'd have to add pi. And then to get back there, another pi. And then back there, another pi. So I would say start at pi over 2 and then add to it what? Pi k. Right? If this ever happens, this tangent is undefined, right? So when I say domain, what I want to say here is this. I want to make sure that the thing you plug in, right, the x you plug in, make sure that it's never any of these. Do y'all see how this is a lot more complicated in terms of domain than this is? Like this, yes, you can plug any number you want into sine. Yes, you can plug any number you want into cosine, right? No issues. But here, we have to be very careful not to plug in any angle that lands here or here. How do you say any angle that lands here? There. So we want to make sure that x is not that, right? That clear? All right, what about the range? Pretty much what? It's everything. Very good. So look at the outputs. Bless you. So you know how here we were stuck between negative 1 and 1, but here, because tangent goes up forever and down forever, all outputs are possible. So the range of this is negative infinity to infinity. Questions there? How about period? Do we still have a concept of period with this? Yes. How large is this interval before it repeats itself? Pi. So pi over 2 this way, pi over 2 that way, so the total would be pi. How about amplitude? Well, amplitude over here was like the distance between the x-axis and that peak. Or you could say this total distance divided by 2. But here, our range is everything, right? So there's no amplitude. It doesn't make any sense to talk about amplitude of a tangent function. Tangent functions don't have amplitudes. Yes?
So the domain, after plus pi k,
Okay, yeah, good question. So in this class, if you put plus pi k, I will understand that you mean k is an integer. Okay, you don't need to state that. In general, in another class, you should be clear on that. But in calculus, it's usually understood that k or n are both integers. So you don't need to state it on test. I'm not going to take off. All right. Any other questions? Yes.
As far as the domain,
Yep.
for instance, at homework, you're listing it as like interval.
Yes.
Is there a way to write that in the notation?
You can, but it's not easy to write it that way. Sometimes it's easier to tell me what it can't be than to try and tell me what it can be. And I think this is the most efficient way to do it. So don't worry about the computer. This is what I've said, I think, before. Last class I was telling you how I get frustrated with the computer because I would never ask you to give me the interval notation for the domain. I would say, tell me what it can't be. That's the easier way to go, right? Okay, let's look at the next one. What's our next function? Let's go to cotangent, right? So cotangent is very similar to tangent in the sense that it kind of looks the same, except we've got problems at 0 and at pi, or where we have the issues. Pi over 2 is where we have the x-intercept. And the picture looks like this. So let's talk about, well, we have domain. Let's talk about range. Let's talk about period. Let's talk about amplitude. Let's do range first. I think range is easy, right? It's the range of the cotangent function. Everything, right? All real numbers. Negative infinity to infinity. How about the period? Pi as well, right? 0 to pi. Amplitude. Doesn't make sense, okay? All right, domain. This is going to have problems in a lot of different places, isn't it? And we can do it by the same way we did it a second ago. We can say, what is cotangent? By definition, cotangent is tangent flipped over, right? So it's x over y. So we're going to have problems whenever y is 0, which is going to happen here and here, at 0 and at pi, right? But we want to represent all of those answers. So how do we represent all those answers? So we would say here, if we're going to talk about domain, the x cannot be what? Pi k. Right? What did you say?
I said pi plus pi k.
Or you could say pi plus pi k. You could start at pi and then add to it pi k. Or you could start at 0 and add pi k. They both give you the same thing, right? You can say 0 plus pi k. That start at 0 and then just start adding half rotations. Or you could start at pi and add pi k as well. That's correct. This is a correct answer as well. You could start at 100 pi if you want and add pi k. It doesn't matter where you start as long as you start here or here. That makes sense? So any of those are fine, but I think this one's the cleanest one, right? Take the 0 off, just pi k. So we want to make sure it's not pi k. Good? Okay, 2 more. So just to give you a heads up, what we're trying to achieve honestly in this class, as somebody who teaches Cal 1, Cal 2, Cal 3, right? What I want to be able to do is get you into a Cal 2 class and be like, okay, we've got tangent to 4x. And you can kind of visualize what that function looks like without having to like spend 30 minutes trying to graph it. Like you understand, tangent of 4x would be, you know, you could set the argument 4x equal to those critical numbers here. You could tell me real quick where we've got some verticals. Does that make sense? Like should be a quick thing. You should be able to talk about domain and range, right? That's what the real goal is here, is for you to have a foundational understanding of what the graphs of these things look like, so that in calculus, we can reference them quickly. Talk about their behavior. What's happening? Oh, it's going up. Oh, remember, it's going to be going down. Or, oh, that's that U You know what I mean? Just the shapes we need to be familiar with. All right, let's go cosecant. So this graph, basically this is just your sine curve, right? Everywhere you have an x-intercept, you've got a vertical. And at the peaks, you go up like a U like this, and at the valleys, you go like that. Right? That's it. That's what cosecant looks like, basically. Can you talk about domain of this? Okay. So tell me about it. Is it? Except for, we got a bunch of places where it's undefined, don't we? Isn't it? It's undefined everywhere that sine is 0, yes? And by definition, on the unit circle, sine is which coordinate? The y coordinate. So wouldn't we have, wait, hold on. Sine is the y, right? So we would have undefined where?
Wait, no.
Hold on, I'm having a complete like crazy. Look at, yeah, no, this is right. Okay, look at this right here. We have 0 here, pi here, right? 2 pi. Yes? That's where our verticals are. That corresponds to where the sine function is 0. These x-intercepts of the sine function. Sine is 0 where? Here and here, right? What are those? Pi k. We just did that, right? In the previous. So wouldn't the domain be everything except those points? So the domain here would be x is everything except pi k again. So these are very similar domains, aren't they? They're different pictures, but they're similar domains. What about range? Ooh, this is the one that gets people. The range. It's not -1 to 1. It's not all real numbers either.
Negative infinity to -1 union.
Okay, so negative infinity to -1 bracket union 1 to infinity. Okay, so let's talk about what's going on here. Look at this u right here, this one here. That starts out at a y value of 1, doesn't it? 1, and then it goes up, doesn't it, forever? So that's 1 to infinity. That's this right here, 1 to infinity, yeah? The y values, because we're talking about range, we're talking about the y values. So from 1 to infinity, and then this is -1, isn't it? And the u goes down, so you get all the negative numbers below -1, which is this interval, negative infinity to -1. But you do not get 0. Like you could never get 0 out of the cosecant function, right? Like you're never going to hit the x-axis. On the black function, we'll never hit the x-axis. So that's why you can't say negative infinity to infinity, because there are some numbers in the middle there between -1 and 1 that you'll never reach. Make sense? Also, there are brackets. You will actually hit -1, you will hit 1. Like those you will achieve those values. Questions there? We have one more function.
So there's no period.
Oh, sorry, period, yes, thank you. Period? Yes, it is periodic, because it'll do up and down, and then it'll repeat it. Up and down, and then do it again. Up and down. Okay, so the period is still 2 pi. In other words, the period of cosecant is the same as the period of sine, because sine is what dictates what cosecant looks like. Amplitude, there is none. Question?
How come it would be pi even because of the amplitudes? I mean, not the amplitudes.
Oh, because it's got to repeat itself, right? And if one part goes up and the other goes down, those are not the same thing. So it goes up, down, then you'll have up, down again, and then up, down again. So this is one period where it does the entire pattern. Does this make, it has to go up, then down. That's one period. Then up, then down again. And then another period. Up. They're together, yeah. Last picture. We'll do this one on this one. All right, so the last one we have is secant, right? So secant x, the picture of this, we get by drawing cosine, right? We draw cosine in here. Everywhere that cosine hits the x-axis, we have a vertical. And then we have this little thing going like that, this little u in here like that, and then like that. What do we have here? How about domain? This domain's a little bit harder. Or is it? Secant is 1 over cosine. So anywhere that cosine is 0, we're going to have a problem, right? Anywhere that cosine is 0. Where's cosine 0? Pi over 2 and 3 pi over 2. So the top and the bottom of the unit circle. Did we ever have that anywhere here? Oh, I think we did. Right here, this one, right? This is the same issue. This was pi over 2 plus pi k. That's pi over 2 and then a half rotation. So our domain of secant should be the same as the domain of tangent, right? So x cannot be pi over 2 plus pi k. What about range? Exactly, it's the same as cosecant. It's everything up to -1, then everything past 1. So negative infinity to -1 union 1 to infinity. How about period? 2 pi. Because it's cosine, right, is what's controlling the secant function. Does seeing them all together here help you kind of sort it all out in your mind, like the difference between these and like what's important for each one of them? Yeah? Okay.
What I'm not understanding is
Yeah.
how did the cotangent shift?
Okay, so by definition, right? By definition on the unit circle, tangent is y over x, right?
Yeah.
So cotangent of some angle would be the x over the y. And so if you look at where the, why did I put cosine? Cotangent, sorry, would be the x over the y, right? This is going to have a problem wherever y is 0. So here and here, right?
Okay.
That's where cotangent has problems. At 0, at pi, at 2 pi, at 3 pi, at 4 pi, it's, right? As opposed to, tangent, right? Shit, tangent. Well, where does tangent have a problem? Tangent is y over x, right? And so where's that going to have a problem? That's going to have a problem whenever x is 0, right? Which is here and here.
Okay.
See, not these two places. So that's why it's not, they don't have the same vertical asymptotes. Vertical asymptotes for cotangent are at multiples of pi, and the vertical asymptotes for tangent are at pi over 2 plus a half rotation either way.
Okay.
That make more sense?
Yeah.
Any other questions? Yes? Yes. No problem. In Cal 1, I'll show you right now what my Cal 1, the formula sheets for Cal 1. I'll zoom in on this. These are the formula sheets that my Cal 1 students are allowed to use. And there's a page here, where is it? Did I already pass it? Oh, there it is. There's a page here, right there. Do y'all see how I have, it has the graphs of the trig functions? Just as a kind of summary, as a reference. Here's sine, 0 to 2 pi, right? Here's cosine, tangent, right? Cosecant, secant, cotangent. It reveals enough information for you to remember certain things. It doesn't give you everything. It doesn't give you all that, right? But it gives you enough for you to kind of have a general idea of what they look like, right? Okay. Any questions? All right, why don't we yeah. I want to show you a problem, like a real world problem where you would see one of these like cosecant or secants come into play. Like when would you ever need a cosecant function or something like that, right? How are we doing time-wise? All right. So let's say, I'm going to draw a picture first. Let's say that we're looking from the top down and there's a person standing here. So we're looking, that's their head, okay? And let's say this is like a, what do you call it? Like some sort of abyss that we can't cross through over, okay? So like a Grand Canyon. We're standing on one side. On the other side, there's going to be a person, okay? And this person's going to, and let's say the distance between here and here is, I'm just making this up, 40 feet, all right? And this person's going to start walking this way. And let's imagine this goes forever, okay? So this is a totally like hypothetical situation, right? This goes forever in both directions. And this person's going to start going this way. And what I like for us to do is this. Find a function, or find the distance between the people as a function of theta. So I have to draw something here for you to kind of understand what's going on. I haven't drawn theta on this. I'm going to draw it. So imagine this person starts walking, okay? And they're going to be somewhere down here, right? That's the person. And I'm going to measure theta to be, what do I want it to be? Let's let theta be this angle right here. All right? So I'm standing there. Initially, I'm looking across. There's my friend. And they start walking, right? And as they start walking, I can kind of track them, right? Like this. And I'm measuring the angle here between them, my line of sight from me to them, and then this wall, or this imaginary line, okay? I want you to calculate the